Welcome back, everyone, to Math 098 Elementary Algebra. So we want to continue working on understanding the substitution method for solving systems of equations. Good morning, Kayla. So we're going to continue with that with a couple problems. Just to take a look, make sure we understand exactly how to use the substitution method, and then we'll move into elimination. And like I said before, you'll find that elimination tends to be really, really nice, and it might actually be your preferred method for solving systems. However, don't think that you'll never use substitution. There are many instances where you'll be presented with a system of equations and it just makes sense to use substitution. So with more practice, I think you're going to recognize that right away. All right, so let's take a look at continuing with the substitution method. All right, number 3, we have 2x plus 3y is equal to 6, and we have 4x plus 6y is equal to 12. So as we discussed last time, it's going to be essential to isolate one of the variables of your choice. And one of the things we noticed is that we would pick a term that had a 1 as a coefficient, but unfortunately that's not the case here. Not a big deal. So what I'm actually going to suggest is maybe isolating one of these two terms. So I'm going to isolate the x in my first equation, just because I feel like that might be the best approach, not that it matters whatsoever. So let's take the first equation, 2x plus 3y is equal to 6. And remember, we're using substitution. So I'm going to subtract 3y from both sides. That leaves me with 2x is equal to negative 3y plus 6. And then I'm going to isolate x by dividing each term by 2. Unfortunately, this is going to leave me with one term that has a fraction, but honestly, don't overthink it. It's not a big deal. So we found that x is equal to negative 3 over 2y plus 3. So that expression is x. So what we're going to do is we're going to write the second equation, 4x plus 6y equals 12, and we're going to recognize that this expression here is going to replace x, because x is negative 3/2 y plus 3. So we're making this substitution. You'll notice I like to write all of these individual steps. That way when you go back in your notes, you're like, ah, yes, I know exactly what I did. So if we replace x with negative 3/2 y plus 3, we are sure to write it within parentheses. So we have 4 times the expression replacing x plus 6y is equal to 12. Naturally, you all know that your next step is going to be to distribute. So let's distribute to both terms. We have 4 times negative 3 over 2y. Again, if you're ever uncomfortable with fractions, just do a little bit of side work. It's not a big deal. So 4 times negative 3 over 2. Let's put that 4 over a 1. I hope you notice that because we're multiplying these fractions, we're actually allowed to reduce numerator for denominator. So I'm going to divide a 2 out of the 4, leaving me with a 2 out of the 2, leaving me with a 1. So that leaves me with 2 times negative 3, which is negative 6. So this gives us negative 6y. 4 times positive 3 is positive 12, plus 6y is equal to 12. I always try to combine like terms. Doc, no big deal. Thank you for letting us know and welcome. I always try to combine like terms first before moving terms from one side of the equation to the other. Negative 6y plus 6y, these are actually opposites. So when they cancel each other out, they leave you with a 0. And 0 plus 12 is simply 12. So look at what we're left with. 12 is equal to 12. This is a yes statement. This is something where we'd be like, oh yeah, that's definitely true. 12 is definitely equal to 12. And then what that brings us back to is this idea of identity, right? Where the left side is equal to the right side. Notice here that this is a true statement. So actually our answer in this case is going to be infinite number of solutions. what that means, and I'll circle this because that's our answer. What that means is that this system is actually dependent. Dependent system. And again, furthermore, that means that they are the same line. So these two equations, 2x plus 3y equals 6 and 4x plus 6y equals 12, they're actually the same line. Now, if you looked at these two equations and you thought, they don't actually look all that different, and you looked closer and you said, whoa, wait a second. If I take the first equation and I double it, that gives me the second equation. So you mean if you took the first equation, 2x plus 3y equals 6, and then you doubled the whole thing, meaning you multiplied every term by 2. Remember, we're allowed to do this. It's an equation, and we're doing that to every single term. That leaves us with 4x plus 6y is equal to 12. Oh, these are the same. So we know that in this particular system, the two lines are actually the same. Now, to kind of speak to this, if you were, let's say, taking an assessment, or whether that be a homework or a test, and you looked at the system and you're like, whoa, the first equation is just half of the second one. So they're actually the same line, and you notice right away, go ahead and say infinite number of solutions. It's a dependent system, right? Because they completely overlap. They're the same line. If you want to show the steps to prove that this is a dependent system, then go for that as well, okay? So really, it depends on your style and what you recognize right off the bat. Let's take a look at number 4. For number 4, we have 3x plus y is equal to 8, and 6x plus 2y is equal to 9. Again, what we're going to do is focus on solving for a variable of our choice. And it doesn't matter which one, right? But what I'm going to recommend is that your first equation, hi Rachel, for your first equation, you can easily get y by itself. So I'm going to give you a couple minutes. Use substitution, and then in the chat, tell me what you get. Go for it. Okay, so we agreed that we were going to take the first equation, and we were going to isolate y. We are going to get y by itself. We're going to do that by subtracting 3x. That leaves us with y is equal to negative 3x plus 8. We're then going to take this expression and plug it into the other equation, the 6x plus 2y is equal to 9, because we didn't manipulate that equation. If you manipulate the first equation, you take the expression and you plug it into the second, okay? It is a system of equations, so they must work together. Notice that y is a negative 3x plus 8, so where the y is, you replace it with this expression. Ria, so that statement, tell me what that means to you. So you have a result. Now tell me what that means. So we're going to go ahead and replace y with negative 3x plus 8. And then, of course, we have 6x plus 2 times a negative 3x plus 8 is equal to 9. Our next step would be to distribute. That gives us 6x minus 6x plus 16 is equal to 9. So what Ria shared in the chat was that our like terms, 6x minus 6x, those cancel, leaving you with 0, and 0 plus 16 is just 16. So then she shared in the chat, 16 is equal to 9. Well, that's really interesting. Is 16 equal to 9? Am I allowed to say, hey, Ria, I know that I owe you 16 bucks, but that's the same as 9, so we're good, right? No, that's absurd. So 16 does not equal 9. Having said that, this is a no statement. This is like, what? No way, right? So in which case, that means there is no solution. The only scenario in which you have no solution, yes, Ria, perfect. The only scenario in which you have no solution is if the lines never intersect. This is called an inconsistent system. And we know that the two lines never intersect, which means they are parallel. Okay? If the two lines never intersect, they are parallel. So Ryan, you asked would it be correct if you solved 4x. Now the issue is your 6x and your negative 6x, they actually cancel each other out. So you wouldn't have a solution anyways. Even if, let's say, you started from the beginning and you isolated x instead of y, when you made that substitution, you'd still be in the same place. You would still be in that same situation where you made the substitution, but then the variables, they end up canceling each other out. And then it leaves you with a false statement, like this 16 is equal to 9. Not true. So regardless of the approach that you took, you'd actually see the same thing. So just be careful with when your variable terms cancel each other out, they leave you with a 0, right? Not an x, not a y. It literally leaves you with a 0. We've seen this a million times. If we had 5 plus a negative 5, you would say, well, that's 0. So that doesn't change if there's a variable. So 5m plus a negative 5m, 0, right? So keep that in mind as you do these problems. If they eliminate each other, they eliminate completely. We are now ready to look at elimination method. I really do think that you will enjoy this method. I'll try to break it down the best way that I can first, but I find that when you see the actual problems, the examples, then you get this sense of, oh, that's what she's saying. Okay, so let's take a look. I'll run through the rules anyways, and we'll see a bunch of examples. Elimination method. Okay, so when we use elimination method, we actually want our equations in standard form, right? So the rule number 1 would be, let's rewrite equations so that they are in standard form. This is going to be the best practice for you, just to make sure that you're following this to the T. Notice here, I have 4x minus 2y equals 14, and I have a negative 3x plus 5y equals a negative 14. These two equations are definitely in standard form, right? So ax plus by is equal to c, where a, b, and c are real numbers, and x and y are your variables. Okay? Now, step number 2 says choose which variable you want to eliminate. Now, the cool thing about this is you can choose if you want to eliminate x or if you want to eliminate y. It's totally up to you. So what I've done in my example problem here is I've chosen to eliminate x. All right, so we've made that decision, eliminate x. Now, step 3 says find a common multiple for both terms with the same variable. Okay. Now, if you look at 4x and you look at negative 3x, I want to eliminate the x term. So I need a common multiple of 4 and 3. A common multiple of 4 and 3 is 12, right? Because we have 4, 8, 12. We have 3, 6, 9, 12. So they both have a common multiple of 12. Next, if necessary, multiply one or both of the equations by a factor that will make the chosen variables the multiple you found from step number 3. You may have to multiply by a negative number to ensure that these terms are additive inverses or opposites of each other. So the first thing I notice is that I have a positive 4x and a negative 3x. So they're already opposite signs. That means I want this first term to become a positive 12x and this second term to become a negative 12x. In order to make that happen, notice that I have to take the entire first equation and multiply by 3. That is one of the rules that we learned from chapter 2. If you choose to multiply or divide in an equation, you must multiply or divide by the same quantity to every single term. Okay? Every single term. This idea never goes away. Think back to chapter 2. We're going to do it again here. So check it out. So we choose 3 to multiply the top equation by, so that when I distribute, I get 12x, which was the goal, then a negative 6y, and then a 42. Do you see how we have the 12x minus 6y equals 42? Our second equation, I multiplied by a 4, because again, I'm looking for 12s, right? I'm looking for a coefficient of 12 for both of my x terms. So when we distribute, we get negative 12x, positive 20y is equal to negative 56. This is great so far. Now, once we've gotten both of our equations in the right form, meaning once we have our term that we're going to eliminate as opposites, then we can actually combine the two equations by using their indicated operation. 12x minus 12x, that's a 0. They wipe each other out. Negative 6y plus 20y is a positive 14y. 42 minus 56 is a negative 14. By the way, if there were no signs here, they're both positive, which means you would just add. Okay? Keep that in mind. So then we have 14y is equal to negative 14. Well, we know how to solve for y. We just divide by its coefficient. So we get y is equal to negative 1. And here's one of our coordinates. Remember, the solution to a system is always going to be x then y. So at this point, once we have one of our solutions, we actually can plug it into both of the original equations. Notice here I plugged in y equals negative 1 into our first equation from our system. I can actually also do that for the second equation in our system. So we are saying that y is negative 1. And I want to show you this. So we're going back to the method that we used for substitution. Notice here we have 4x minus 2 times negative 1 is equal to 14. Negative 2 times negative 1 is positive 2. Subtract the 2 to get 12. Divide by 4, and you get that x is 3. I'm going to prove that on this side. So we have negative 3x minus 5 is equal to negative 14. I'm going to add the 5. That leaves me with negative 3x is equal to negative 9. I divide by negative 3, and I get that x is 3. So the solution would be that ordered pair 3, negative 1. Now the great thing about taking the y equals negative 1 and plugging it into both equations is that this serves as a check. If they both equal the exact same value, then you know you did this correctly. Okay, you can always plug into both of the equations with the 3 as x and the negative 1 as y anyways, and do a check, so it's completely up to you. By the way, this should be an equals. I'm sorry for that typo. 14 equals 14, which is a check. Okay, that was a mouthful. Let's see this in action, and I really, truly believe that you're going to love this. Okay. Solve the following systems by using the elimination method. The first thing I'm going to do is I'm going to rewrite the system. 3x plus 5y is equal to negative 6. Negative 2x plus 7y is equal to 4. I would like you all to do the same thing. Rewrite the system. Now, taking a look at your paper, if you wanted to eliminate x, what is the common multiple of 3 and 2? And then, if you wanted to eliminate y, what is the common multiple of 5 and 7? Well, when we think about this, we can say, well, the common multiple of 3 and 2 is 6, right? So if I wanted to eliminate x, my goal would be to make this first term a 6x and this second term a negative 6x. Now, what if instead I wanted to eliminate y? Well, a common multiple of 5 and 7 are 35, right? So I'd have to multiply the top equation, the entire top equation, by a positive 7. And actually, I'd have to multiply the entire bottom equation by a negative 5. I need one of these to be negative. It doesn't matter which one. I just selected that the bottom one would be negative. But that's completely up to you. So we have a lot of options here. What I'm actually going to do is I'm going to say, let's eliminate x. Okay? If we eliminate x, the goal is to make these 6x and negative 6x. That's the goal. We want our first term to be 6x and our second term to be a negative 6x. Well, that's a piece of cake. If you take your entire first equation and you multiply it by 2, take a look. So we're going to draw the lines of distribution. Please do the same thing. I'm trying to go nice and slow so that you can literally follow every single little thing that I'm doing. These are good habits to get into, I promise. The second equation, you're going to multiply by a 3, because remember, you want this to be a negative 6x, and we do that by multiplying by 3, which means we must distribute to each of those terms as well. No problem, Doc. So now, check this out. What I would like you to do is to show the distribution here. As you work on your page, sometimes it's helpful to be given a strategy in terms of what it should look like. What I like to do personally is I like to work from left to right. The same way that I read, I like to work from left to right. So check this out. 2 times 3x is 6x. 2 times 5y is positive 10y. 2 times negative 6 is negative 12. We're going to do the same thing with our second equation, and I'm going to stack it directly underneath, right? We're moving from left to right. 3 times a negative 2x is a negative 6x. 3 times positive 7y is positive 21y. And then 3 times 4 is positive 12. And let's draw our line here. So once we have distributed by, once we've multiplied by that factor that gives us that common multiple, and we distribute and we have those two equations that are stacked, and again, they're both in standard form, we can now combine these two equations using the indicated operations. So first off, 6x minus 6x is 0, so that goes away, and 0 plus whatever this is stays whatever this is. We have a positive 10y plus 21y. That gives me a 31y, right? Remember, 6x minus 6x is 0, not 0x, just 0. It's helpful to not include the x with your 0 because you'll be less likely to keep the x there. So just think you had 6 x's and somebody took them all away, so you have nothing left, okay, in terms of the x. Then we have negative 12 plus 12. Well, negative 12 plus 12 also cancels out, but because we need a placeholder, we're going to say that that's equal to 0. We know that it equals 0. Negative 12 plus 12 is 0. So I'm not just going to leave this as an empty space. That would be silly. So now we have 31y is equal to 0. Okay, we're going to divide both sides by 31. And 0 divided by 31, guess what, is 0. Which is a valid coordinate, right? We have had zeros in our y. I want you to think about where that might be. Now, we're obviously not done. We are going to take our solution, which is y is equal to 0, and plug it into one or both of the original equations. Again, it doesn't matter if you plug it into both. If you do plug it into both, that's a way to check it to make sure that you did it correctly. So because it won't take too long, I'm actually going to plug it into both of the original equations to prove that we get the same answer. So we have 3x plus 5 times y, but y is 0, is equal to negative 6. And then we have negative 2x plus 7 times 0 is equal to 4. So we literally are taking this y is equal to 0, and we're plugging it into each of the original equations. 5 times 0 is 0, and 0 plus 3x is just 3x. Divide both sides by 3, and we get that x is negative 2. Let's see if it ends up being the same over here. Negative 2x plus 7 times 0, well, 7 times 0 is 0. 0 plus a negative 2x is just a negative 2x. Divide by negative 2, and what do you know? You get that x is negative 2. So the solution is a negative 2, 0. Remember, it's always x, then y. That means that when we graph these two lines, they cross at the point negative 2, 0, which happens to be the x-intercept. Not bad, right? You can visualize where negative 2, 0 is on a graph. Okay. I'm going to give you an opportunity to do number 2, but I just want to make sure that we're all on the same page. So if you look at number 2, we have 4x plus 5y equals 3, and 2x minus 3y is equal to 1. I'm actually going to guide your first steps in this problem. I would like you to eliminate y. And I want you to look at these two and tell me on your papers, write down what these have to become. Think of common multiples, what they have to become. So similarly to what we did here, and then follow the exact process that we just took for problem number 1. When you are done, please share your work in the chat. And I would like to hear from Doc. I would like to hear your perspective. Kevin, I would like to hear your perspective. And let's do Ashanti. I would like to hear your perspectives, okay? Go for it. Give this your best shot. All right, we are ready to check this out. So if we have a 5y and a negative 3y, a common multiple of 5 and 3 is 15. So we want our first term to be a positive 15y and our second term to be a negative 15y. So with that in mind, we are going to first rewrite our equations. 4x plus 5y is equal to 3, and then 2x minus 3y is equal to 1. We're going to multiply the entire top equation because we want it to be a 15y. We're going to multiply the entire top equation by 3. Thank you, Kayla. And then for the second equation, we want a negative 15y. It's already negative, so that means we're going to multiply the second equation by 5. Let's distribute. Again, it's very helpful to show the lines of distribution so that you don't forget to multiply every single term in the equation on both sides by that coefficient. So that leaves us with 12x plus 15y is equal to 9. Then we are left with 10x minus 15y is equal to 5. Let's combine both of these equations. So we have a positive 12x and a positive 10x, which gives me a positive 22x. 15y minus 15y, that leaves us with a 0, but 0 plus 22x is still 22x. And then a positive 9 and a positive 5 gives us a positive 14. We are then going to divide by 22, and we notice, oh, I can reduce this. If I reduce this, I get that x is equal to 7 over 11. Very nice. Yes, Ria, excellent. Very nice, all of you who have typed in the fact that you found that x was 7 over 11. Okay, so now here comes the time where we could do a couple things. The first thing you probably did was you took the 7 over 11 as your x and you made a substitution into one or both of the original equations. Now, the really cool thing about the elimination method is that what if I started again and instead of eliminating y, I eliminated x? If I restarted this problem and decided, I want to eliminate x instead, we can actually solve for y. So this takes away from having to make that substitution. So it's an option. I just want you to know that it is an option. What I will do, because you already know how to start the problem again and eliminate x instead of y, is I will make that substitution just to show you exactly what it looks like. Okay? So we're going to substitute 7 over 11 into both of the original equations. So this is one of our solutions, right? So we have 4 times 7 over 11 plus 5y is equal to 3. And then we have 2 times 7 over 11 minus 3y is equal to 1. So I'm making this substitution into both of the original equations. 4 times 7 over 11, remember that's over a 1. So 4 times 7 is 28. 1 times 11 is 11. So 28 over 11 plus 5y is equal to 3. Now, I don't know about you, but I don't really want to have to deal with fractions, so I'm actually going to multiply every term by 11. Look at all the strategies we're able to take here. The 11s will divide out, so that leaves us with 28 plus 55y is equal to 33, because I multiplied by 11. So let's solve. We're going to subtract the 28. That gives us 55y is equal to, and then 33 minus 28 is a 5. When we divide by 55, we notice right away that we can reduce this. So if we divide both of these by 5, this becomes 1, my numerator becomes 1, and my denominator becomes 11. So my y value should be 1 over 11. I'm going to solve in this second equation as well, just to make sure I get the exact same thing. So again, 2 over 1 times 7 over 11 is 14 over 11. Same thing, I don't want to have to deal with adding or subtracting fractions, so I'm just going to multiply every term by 11. My 11s divide out, that leaves me with 14 minus 33y is equal to 11. I'm going to subtract the 14, that leaves me with negative 33y is equal to negative 3. Divide by negative 33, and what do you know? You get y is 1 over 11. So your solution for this problem is 7 over 11, comma, 1 over 11, x, then y. Excellent. Very, very nice. I'm hopeful that this made a lot of sense, and I'm hopeful that you're comfortable with the strategies I took to solve for the other variable. So as a reminder, we could have started again. So I actually want to demonstrate that, and that'll end our class. So what I'm actually going to do is I'm going to rewrite the original system, but this time I'm going to eliminate x instead. So check this out. So my system is 4x plus 5y is equal to 3, and 2x minus 3y is equal to 1. Okay, here's my system. This time, instead of eliminating y, I'm going to eliminate x. So I have a 4x and a 2x, and a common multiple of 4 and 2 are 4. So I want a 4x and a negative 4x. That's my goal. I want a 4x and a negative 4x. So I'm going to rewrite each equation just like I've done before. And I have to decide if I want to get a 4x. Oh, wait a second, they're the same. So if you wanted to, you can just say you're multiplying by 1. You don't need to do this. You're not required to multiply each equation by a constant. But just to showcase what's happening here, I'm going to write that I am multiplying by 1. Now, I want my second term, this 2x, to become a negative 4x, which means I'm going to have to multiply by negative 2. All right, let's distribute. Draw your lines of distribution throughout. 1 times 4x is 4x. 1 times 5y is 5y. and 1 times 3 is 3. Negative 2 times 2x is negative 4x. Yay! Negative 2 times a negative 3y is positive 6y. And negative 2 times 1 is negative 2. Notice 4x take away 4x. These cancel each other out, leaving you with 0. 5y plus 6y is 11y, and 0 plus 11y is just 11y. And then 3 minus 2 is 1. Divide both sides by 11, and there you have your y. I am hopeful again. I'm always hopeful. I really hope that made a lot of sense. I want to give you strategies. I want to give you options. So if you're in a position where, you solved, you found that your answer was a fraction, and you're like, I just want to start again and eliminate the other one, you totally can. And that will give you the corresponding coordinate, okay? Those two answers together, the two coordinates together, make an ordered pair, and that represents the point of intersection for that system. Excellent, Doc. I'm so glad. I just want you all to have that in your toolbox. On that note, we're done. So I will see you all tomorrow. We'll continue with this idea of elimination, and we are ready to move into word problems. Yes, I said it. I'll see you all tomorrow. Bye.